Yes, I'm going to be taking over all of your browsers for fun because I can. A little bit about myself. I'm James. I like doing stupid things with Ruby and JavaScript, and I wrote a bunch of open source stuff that you might have heard of. Most important thing about this talk is that there is audience participation. As I'm sure you'll have seen me tweeting for maybe weeks. If you have a Macintosh computer, that's one of the ones that's got this little apple on the back, and Firefox, a recent Firefox, so 6 or 7, I need you to open it and go to this URL. And then don't do anything, don't click on anything, don't sign into anything, you just have to open that URL, and the reason why will become clear shortly. And keep your volume off for now. So, some backstory. Why am I doing this? This is a band called the Flaming Lips. I'm sorry? Everyone got that? Okay, turn your sound off. Thank you. Awesome. So yes, this is a band called the Flaming Lips. They're mostly famous these days for filling stadiums with balloons and confetti and lots of weird noise. But back in the 90s, they released this album called Zyreka. Zyreka came on 4 discs that you were supposed to play at the same time. They're assuming that people had 4 stereos lying around. And the idea was that, like, this gave the user some control over, or listener rather, some control over the sound, but it also took advantage of the fact that CD players aren't perfect. Their clocks all track at different speeds, and they don't track constantly. Like, the same CD player doesn't maintain constant time very well. So all the samples on these discs would kind of get in and out of sync with each other, and you'd get interesting effects, and like the gaps between tracks would be different on each machine. And so they were kind of using multiple outputs to do something interesting. This is a band called Boredoms from Japan. They're a noise rock band. They're extremely noisy. They have a 7-neck guitar. They have this array of things that I don't know what they're called that this dude beats with sticks. In this picture, there's at least 1, 2, 3, 4, well, there's actually 77 drum kits. This is a show they put on the 7th of July, 2007 in Brooklyn. They got 77 drummers from a bunch of alternative rock bands and played a bunch of their material. And it was this crazy mix of kind of like just chaos, and then when they all actually start deliberately drumming together, it's just this tremendous, it's like this giant robot marching through. It's incredible. I've only seen them with 7 drummers, but that was staggering, so I assume this was just, I'm surprised the earth didn't blow up. So, skip forward a few years. I'm sitting at Hack Day in San Francisco, and I'm kind of tired of gluing together web services, and I want to make some music. So I am, I'm kind of looking around for people who know how to do synth stuff, because I know nothing about it. And I'm not getting anywhere with that. And then I think, hey, there's a bunch of other computers here. What if we could make them all make music? And so I put together this really simple little synth. It was monophonic, it had really basic controls, it couldn't do very much. But we got a room full of computers to play Happy Birthday to one of the organizers. And it sounded just about recognizable. But yeah, it worked. So I want to go away and do something more sophisticated, something where you could record stuff, play loops, play chords, do effects. And that's what I want to show off today. I have to confess, when I proposed this talk, I didn't know what it was going to turn into. I just wanted to get hundreds of laptops together. And, but I've learned something by building this, so hopefully you guys will get something out of it too. So that is where this project came from. So I'm going to try and do a demo. If this works, I'll be tremendously surprised, because it has a very high chance of not working at all. So let's just take those down. Yeah, if you guys could like refresh your browsers actually, because it's probably fucked up already. Yeah. Oh wow. We all refreshed? Okay. Okay. So I'm just going to try and get a couple people to play this one sample. We've got a couple people playing that. Yeah, can you turn your sound up now? If they start buzzing, just refresh. Oh. How do you feel connected right now? I'm not sure these are syncing up terribly well, are you? I'm going to cut that up. All right. So a few of them are kind of synced up. So you can do stuff like bring in more samples. No one's going to pick that up. Okay, so it turns out it sounds terrible. But never mind. Thanks, everybody, for helping out with that. This is what happens when you don't have hundreds of machines at home to test with. Anyway, okay, sound off. So yeah, aside from it being an incredible failure, I have learned a few things while building this. So the first of which is, how do you generate sound in a browser? This is stuff that's been in Firefox for a while. It's just coming into WebKit and Chrome, and you can programmatically generate sound. So how do we do that? Well, sound is just waves, right? And it's represented in the exact same way digitally. You just have to produce big streams of numbers and write them to something. So this is a really basic sound wave. This would produce just a constant... I'm losing my mic. Yeah, all right, cut it out. So this produces a constant pitch, constant volume, just pure single note, with no effects, no change in volume, no nothing. And synthesizers work by taking these waves and modifying them. And you, just with some really basic modifications, you can make some really interesting sounds. So one thing you can do is use a low frequency wave to change the volume. This is called Amplitude Modulation, and it makes the volume oscillate up and down. If you want to replicate kind of more realistic organic instruments, so the way that, like, if you hit a piano key or you strum a guitar, the note will trail off over time. So the way you model that is that you apply what's called an Adsr envelope to the sound, where you have an attack time, which is how long it takes to ramp up to full volume. You have a decay time, which is how long it takes to trail off to the sustain level. And the sustain level says how loud it is while you're holding the key down. And then there's a decay time that says how long it takes to trail off to silence. And just using that, you can do some quite interesting things. So now we know how to model sound. How do we make browsers spit stuff out? So Firefox has this audio object, which you make a new one of those, and you say, I want 2 channels, left and right, and a 44 kilohertz sample rate, which is a standard sample rate used in digital audio, which means that you have to generate 44,000 data points per second for the sound waves that you're generating. And then you just make a set interval loop that, like, every 10 milliseconds, say. It takes the current time. You get your sound generation stuff to give you a time slice, which is just a big array of floats, which is just a little, slice of the wave function for that interval of time. And then you use the Moz write audio function, and that actually writes it to the speakers. So within your models for generating sound, this is basically what sine waves is doing, is it models things using note objects. And you can ask a note for a time slice, and what that's going to do is it's going to take the current time and the interval that you want to generate and the sample rate, and figure out how many samples you need, and then just build up an array by just going over every little time point in that interval and calculating the value of the wave at that point. Builds a big array and just returns it. And then to figure out the value of a note at any particular time, there's a bunch of maths that I'm not going to dwell too much on. And also, I feel like after Jed Schmidt's talk, I should reduce the size of this tremendously. There's a bunch of math just to calculate what the value of the wave is at that time. But we have a problem, right? Imagine that you assigned a sequential ID to every little bit of data that you wrote to an audio stream. What you want is a just continuous, uninterrupted stream of IDs going through with no sections repeated, no bits skipped. But as we know, JavaScript timers aren't tremendously accurate. If you can say that you want a loop to fire every 10 milliseconds, but it will never actually do exactly that, right? Sometimes it'll be a bit late, sometimes it'll be a bit early. And the code that we had here, that's just getting the current time to figure out what the kind of starting index of your slice is. So what that's going to do in practice is that we might write a couple of loops of just uninterrupted. The first one we do 0 to 9, and then we do 10 to 19, and that's fine. But then the third iteration starts a bit early, so we repeat a bit of the last one. And what that ends up doing to the sound is this, which sounds really, really horrible. If you implement your sound like that, you'll get kind of an overlay of white noise on top of the sound. So what you do to fix that is you just maintain your own counter, right? Each iteration of your loop, you increment the counter of however big your interval is, and use that as the current time. But then you've got another problem, right? Because you basically introduce your own idea of what time is, which is potentially going to differ and drift from real time as you go on. So that means that anything you timestamp in a synthesizer, like when user input happens, what the duration of a note is, what frequency is, all that stuff, you have to base it on your counter, not on the built-in date object, because they will differ and the playback loops won't quite join up properly. So that we can model sound, we need a way of doing user input. It turns out that if you've already got a way that you're modeling sound waves, this is pretty easy, right? You just figure out a way of mapping keyboard input to frequencies, which you can pick whatever you like. For sine waves, I'm just saying like pick a key like A major, and just take all the notes in that key and just map them sequentially onto the keyboard. So when a key is struck, you go, what's the frequency of that key? You make a new note with that frequency, and you timestamp it with the current time. So every note has one of those envelopes that I showed a second ago that decides how its volume varies over time, how it picks up, how it trails off. So you need to tell it when it was pressed and when the key was lifted, so that it knows what that envelope looks like. And when you pick a key up, all you do is you look up the note that key code last generated and timestamp it with a key up time, and then the volume will trail off. And recording works in much the same way. So instead of storing all the audio data that we generate, which is huge volumes of numbers, which would be expensive to transmit and store, all you do is you record the user input, because you can completely reconstruct the sound from the user input. So in this case, instead of making new notes, all you do is you just record some events, right? You say, at this time, this key was pressed with this frequency on this channel. And the same for key up. And what that gets you is just some information that says how long the recording was, which means how, if it lasts 8 seconds, that means every 8 seconds you restart the loop. And a list of events that says which keys were pressed at what times and what frequencies those map to. So then for playback, all you have to do is, in your timer loop, every time you hit a multiple of the recording duration, you just schedule a bunch of these events to play the notes in the right sequence. So now we can play stuff on our own machines, but how do we get that to other people, right? So the setup that I'm using is I'm running Node on the server with Express for handling web requests, so that deals with the saving and retrieving the JSON for these performances. It deals with serving you the pages that you can see. And I'm using Fei for PubSub, and that's all backed up with a Redis database. And you have a really simple JSON representation for performances. So performance is just an array of channels. Each channel has a ton of settings, all those little sliders that you could see. Those all represent parameters that can change how the sound works. So a channel is just an object that has all of those settings in it, and it optionally will have what the settings to tune the keyboard are and whether there's a recording on that channel so you can loop it. So all the browser is doing is it's taking that, sending it to server shoves it in Redis. So if all your domain objects have a toJSON method, you can just really easily use XHR to save and retrieve these things, and you can use phase pub subchannels to get updates. So every time that you change a little setting, that's saved it to the server, and then the server is going to use Fay to push it to all the people who are listening. So this brings me to the kind of main thing that I learned, which you've already seen a demonstration of. Time's kind of hard to get right. It's just nasty, right? As you can see, like syncing clocks is just hard. That didn't work very well. It works, I've seen it work okay on smaller scales with smaller groups, and I have managed to get some quite good numbers out of my clocks, but it doesn't always translate into good music. And if you thought it was over the top for me to invoke Stephen Hawking for this is a problem that cutting-edge science has right now. There are people disputing the faster-than-light neutrinos because they think the guys got their clock syncs wrong. So how are we going to sync the clocks? Well, it turns out there's an established way of doing this in Unix. It's called NTP, the Network Time Protocol. And that uses timestamps that have a 2 to the minus 32 second resolution, which I don't know how useful that is in practice. It turns out that's 10 orders of magnitude smaller than the lifetime of the top quark, which is so unstable that it wasn't observed until 1995 in a custom-built particle accelerator. So I don't know how useful that is, but it's a lot more useful than what we have in JavaScript land, which is just milliseconds, which are, I mean, even the millisecond counts that you get are just inaccurate. You see this with timers, and it doesn't even go down to microseconds or anything. But it turns out, like, for some cases, that's good enough, right? The lesson that I took from Zyreka is that stuff doesn't have to be perfect, it just has to be interesting. And whether it is interesting is a function of, you can't go too outside the range or it just sounds like noise, but it also doesn't have to be perfect. So we can use this. And this is basically what NTP does. You have a client, and the client goes, oh, I want to sync my clock with an upstream server. So what it does is it creates a message, and it puts a timestamp T0 on that message. That's when the client sent the message to the server. And when the server receives it, it puts its own timestamp on it, T1, to say, I got this message at this time. But that's going to be in a different time frame to what the client's using, because their clocks aren't synchronized yet. Then the server's going to hang on to it for a certain amount of time. There's processing that needs to be done. It's not sent back immediately. So it puts another timestamp on it to say when it sent it back to the client, and that's T2. And then when the client eventually receives the message back, it puts a final timestamp on it, T3. Now, if you didn't have network latency to care about, the difference between the two clocks would just be T1 minus T0, right? The client says to the server, I think it's this time. The server goes, it's actually this time, and you just send that straight back. But we have networks, and they have latency, and that can be, hundreds of milliseconds, seconds, depending on, where these things are. So how we actually calculate the offset is that we know the total elapsed time on the client side. That's T3 minus T0. And we know how much time the server took holding on to the message. That's T2 minus T1. And assuming those clocks run at about the same rate over a short time span, you can just subtract those two to get the network round trip time. So you calculate that, you halve it, and you take it, you subtract it from the difference between T1 minus T0, and that tells the client what the difference between the clocks is. So we can use phase pub subchannels to do this, right? We can get browsers to send messages to each other. So the client could publish a message to the time channel with its T0, whatever it thinks the current time is. And then the server can listen on that channel and process it, which we'll see in a second. And the client will also have to subscribe to a channel where it can pick up the responses from the server. So it picks a unique ID, and it listens on a channel that contains that unique ID. So when it gets a message back from the server, it can look at the timestamps on that message and do the kind of NTP algorithm stuff to figure out how much it should adjust its own clock by. So on the server side, the server's subscribed to the time channel, so it's going to receive those messages that the client's publishing. And it's just going to go, OK, well, I'm going to return you the T0 that you gave me, and I'm going to attach my own T1 and T2 of whatever those are. So it's pretty simple, but it basically relies on your network being reasonably responsive. If you have high latency, if you have noisy latency, if you have asymmetric up and download speeds between these two people, that throws the algorithm off, right? It just gets stuff wrong. As soon as you have noise, when it tries to figure out what the round-trip time is, it's going to take half of the total time, and if there's asymmetric up and download speeds, that's not going to be the right thing. And the greater latency that you have in your network, the higher that margin of error gets, and you just get out of sync by hundreds of milliseconds, seconds in some cases. So we're kind of thinking that we have a model like this, right, where browsers can send messages to each other and they're kind of communicating directly. But that isn't really what's happening. They're actually going via a server, right? When you use any pub sub service, the browser is sending a message to a server and the server is going to forward it on somewhere else. So that's already kind of latency that we haven't thought of given our mental model of how this works. But it's even worse than that, because these machines are probably going to be on a Wi-Fi network. Depending on what your Wi-Fi hardware is like, that can introduce huge amounts of noise to your network connection. I tried this out at home using Wi-Fi and putting an Ethernet cable to my router, and the amount of latency that Wi-Fi introduces is horrible. So that's more noise. And every one of these links introduces more latency, it introduces variability, and that all adds up in a really horrible way, so to make this thing kind of unusable. So we currently have a system like this, where we have one master, which is the browser being used by the performer, and we have a bunch of listeners. So all you guys in the audience, the guys at the bottom, and my machine is the machine at the top, and you're all asking me for the current time so you can sync your clocks. What if instead we used a model like this, right? We run a clock on the server. The server can sync with the master, and then all the clients will sync with that clock on the server. So that kind of, it removes some work from the master machine, because it's not having to deal with all these incoming messages, which is helpful because any extra work that the browser's trying to do while it's generating audio is just interference, right? If you update the UI, if there's expensive computations going on, it gives it less bandwidth to deal with making audio, and it makes the sound choppy, and that's why in that interface, for example, there isn't, like I wanted to have like a progress bar that would track how fast through a recording I am. Like if I record on one channel, and then I want to record something over the top of it, I want to make sure I'm in time, so I want to see how far along we are. Just adding that made it completely unusable. All those little updates to the DOM made the sound really choppy, and it was hard to use. So if you introduce this, the browser does less work. And it also means that there's less network distance, basically, between the clients and the thing they're trying to sync with. And the important thing in this kind of situation is not that you're all synced up with the performer, but you're all synced up with each other, because that's what is producing the sound. And it turns out, if you go to this model, depending on your network, I've seen tenfold improvements in syncing. Like I've got like hundreds of clocks on my machine synced within a millisecond using a pub sub server on the other side of the planet. But it turns out that this can also introduce instabilities, right? You can get jumps when if the server gets behind the performer's computer, it can kind of jump forward, it can jump back. It turns out that this particular model is just really bad for producing music. You get, like, even if the numbers look really good out of your clocks, the sound that comes out of your speakers is just noise. So that about wraps it up. You've got a synthesizer, albeit one that didn't work terribly well. It's top-to-bottom JavaScript, client-side and server-side. And just a final little Easter egg, this funky little logo that I made for it is also JavaScript. It's just written using the canvas element and a bit of maths. So thank you all for listening. Do you have questions? No, everybody's just baffled. Okay.
First of all, I didn't think it was a failure. I thought it was totally cool, the demo.
Okay.
So, over here was really good. You should, whatever was going on over here.
I was hearing a mix. I was hearing pockets of good and then pockets of just, oh God.
Oh, really? No, I thought it was cool. It was cool. And also cool when two people playing different things and like that would change. How would you debug that?
Sorry?
I mean, how do you debug that? How would you, I mean, if it's not to your, like, what
That's
exactly
the thing, like, I've been trying to figure this out, like, whether it's possible for a client to tell that it's doing a bad job. Because all it has to go on is whether its clock is synced up properly, right? You could do some stuff like detect that you hadn't received any messages for a while, and maybe tell it to shut up if that hadn't happened, but it's kind of tricky to get clients to shut up if they're not behaving properly. Yeah, ideas are welcome. We good?
Thank you.
Okay, thanks guys.